So, so now I hope that all the students are seeing these slides. Is it okay?
Yes, sir.
Yes.
Okay. So some student asked me this question that how these productions are written here on this slide. So I said that this is just a beginning, so you don't have to worry. We have not reached at that point yet. This is the topic of grammars. When we will reach at that topic about context-free grammar, then we will study, then we will learn how we can write these rules and productions. Until then, you only have to take an idea. You don't have to worry too much about how these rules are written here. This is not an issue at the moment in this introductory lecture. So this is the definition of language, and this is the definition of grammar written according to our discussion here. So for example, I can read the definition of this grammar here. A grammar can be regarded as a device. So this is a device. So that enumerates the sentences of a language. So, so these productions, if this is a device, then I will give some sentence to this device, and then this device will parse my sentence. Then, or in simple words, then this device will understand the sentence which I have given to this device. Understand is a very general word. Actually, the word is parsing. So this device, this grammar will parse that sentence from the beginning to the end, and finally this grammar will show that this sentence is uh, legal sentence according to this grammar or illegal sentence according to that grammar. The decision will be at the end after parsing that sentence into that grammar. So this is basically the function of grammar, or you can say grammar is a device which can enumerate the sentence, which can parse the sentence of a language. Nothing more, nothing less. Not more than something, not more than that sentence, or not less than that sentence. So you will understand these concepts. Until then, you only have to keep only that information which is easy for you. If something is hard for you, you can skip that information, because this is just an introductory lecture, and it will happen with you that some things you will understand and some things you will not understand. So this is quite normal. You don't have to worry. So this is Chomsky, Noam Chomsky. This is that person who presented or who invented this hierarchy, which is displayed here on this diagram. And he distributed formal languages. He distributed formal languages into these categories. Every circle is a category of one language. For example, this circle or this ellipse uh, is for regular languages. So this is also one category in formal languages, that there might be some regular languages, and the machine or the device which can handle those languages is called DFA. We will see that this is what is this DFA. FA is finite automata, D is for deterministic. Anyhow, we will see that what this DFA is. Another category for the languages which would be under the umbrella of this regular languages would lie in this ellipse, and the languages which are not lying in this ellipse would automatically come out to this category in the outer circle, and all those languages would be called as context free languages, and the machine available for that, for those languages, is PDA, push down automata. So what I am trying to uh, give you a concept about different languages are that there is a pool of languages. Some languages will lie under this category of regular languages, Some languages will lie under the category of context-free languages. Some languages will lie under the category of context-sensitive languages, and some languages will lie under the category of recursive languages. After this class, maybe. Uh, so you are seeing four different categories. There are other categories, but you are seeing four major categories according to Noam Chomsky. So if I have a big pool of languages, then some languages will lie under this first category, regular languages. Some languages will lie under this second category, context-free languages. Some languages lie under this category, context-sensitive languages. And some languages will lie under this ellipse or this category, recursively enumerable languages, which is dealt by this device Turing machine. So this is the hierarchy given by the Noam Chomsky. And what is the definition of these different languages? Regular, context-free, context-sensitive, recursively enumerable. Again, we will study all these languages one by one during your course of theory of automata. So at the moment, I am not presenting the definition of these different languages, but we will start properly from this regular languages, and then at that moment you will, or we will see that what is the proper definition of this regular languages. Afterward, we will move on to context-free languages, and then we will study the proper definition and other material of this context-free languages, and so on. So up to that point, you only have to hold. So the next thing, the central concepts of theory of automata, or you can say the fundamental concepts of theory of automata. So alphabet, the definition of alphabet and what alphabet is, we already know. So alphabet is a finite alphabet. When the word alphabet comes, you can normally understand that it is the alphabet set. So an alphabet is a finite, non-empty set of symbols. So alphabet is what? It is a finite, which means limited. Some limit is given there. So alphabet set is a finite, non-empty. Non-empty. So the condition is non-empty set of symbols. It means that there must be some symbol in the set. That's why it is non-empty. And we will use a symbol sigma. Sigma, we will use sigma to represent an alphabet set. For example, if we want to represent a binary set, then we can use this sigma, and we can write it as sigma equal to curly braces, and binary contains two symbols only, 0 and 1. So 0 comma 1. So this is a binary set, binary alphabet set, and we can represent it with sigma. And this is 0 1 is explaining that alphabet set. Another example, maybe I can say that give me an alphabet set for all lowercase letters. Then what you have to answer, you have to write sigma is equal to all lowercase letter. It means from A to Z in small letters, lowercase letters. So this is the curly bracket, and you have to write A comma B comma C and so on up to Z. So this sigma is just representing alphabet set, and what is actually in that alphabet set is on the right hand side. And you can read the other examples by yourself, because I want to speed up the things. So these are the very much simple concepts. Similarly, strings, we have already know, or we have already the knowledge about strings. So strings is collection of words, you can say. So a string or word is a finite again, sequence of symbols, sequence of alphabets, you can say. I'm not saying alphabet set, sequence of symbols chosen from sigma. Sigma is what? Alphabet set. If you have an alphabet set, it means that you have a set and you have a symbols in it. And if you have a sequence of those symbols in a form of a word, then that is called string. So empty string, we can also say that this is an empty string as we normally say in programming languages. So empty string is represented with epsilon or epsilon. So this is the symbol epsilon for empty string. And length of a string W, for example, this X, length of a string W, we can represent it, length of W, and then you can represent it with vertical bars. So this is the mathematical representation, how you can represent length of a string in mathematical form. So length of a string W represented with W bar is equal to the number of non-epsilon characters in the string. Non-epsilon, non-empty characters. So the length of a string is very much simple or very much similar to the concept that is available in your programming languages. Length of a string, you have to count the number of characters, and that is the length of the string. For example, X is equal to 0, 1, 0, 1, 0, 0. So this string is containing 6 alphabets. So X, length of X is equal to 6. And Y, what is the length? 7, maybe 4 and 3, 7. And X, Y, this is what? This is the simple concatenation of the string X and Y. Concatenation of two strings X and Y. So same concept as you have already in programming languages. And then powers of alphabet. Powers of an alphabet. Alphabet or alphabet set. So sigma is an alphabet set. And if you have a representation like this, sigma k, then it means the set of all strings of length k. When you have sigma raised power k, then it means this is an alphabet set, sigma. And from this alphabet set, you can draw strings, but the length of the strings would be k. For example, if sigma is equal to 3, then it means the strings that you can generate from this alphabet string will always contain the length 3. 000 or 111 or 011 or 001 or like that. Another representation is sigma star and sigma star. This is called clean star. So sigma star, it means that you can rewrite this notation as sigma 0 union sigma 1 union sigma 2 union sigma 3 and so on. Here sigma 0 means what? Any student? Sigma 0 means?
Here, sigma 0 means that there is an alphabet set of strings, but the length of that alphabet string is 0.
Is 0. That's right. That's right. So this alphabet set is giving us strings with 0 length, union. This alphabet set is giving us strings with length 1, union, and so on. So star contains alphabet set with 0 length. And there is another example, sigma plus, in which there is no sigma 0. This is the only difference between sigma plus and sigma star. In theory of automata, whenever you will see this symbol star, it means clean star. It means it contains strings with length 0 and more. Whenever you will see this symbol plus, then it means that in this language, the string would be of length 1 and more. There is no strings with length 0 in this sigma plus. This is the only difference between these two notations. And this is a small topic about the powers of an alphabet. And then again, languages. We already know the definition of a language. So L, suppose L is said to be a language over an alphabet sigma only if L is a subset of sigma star. If there is a language, then there must be an alphabet set. So that's why if this is the language, then there must be a alphabet set sigma. And what are the different strings that you can produce from this alphabet set? Sigma star. Sigma star mean all possible strings because it contains strings of length 0 and more. So sigma star means we can produce all possible strings according to the alphabets or according to the symbols available in its set. If the alphabet set is containing 0 and 1, and if there is a sigma star over it, then it means all possible combinations of zeros and ones, including empty string, because empty string has a length 0. So,
Sir,
so,
I have a question.
hmm,
Sir, is it necessary to put the epsilon in every language?
no, no, it
If
is
we
not.
discuss it,
It is not, because when you will see this star, then you can place or you can put the epsilon in the generated strings of that language. Otherwise, if it is sigma plus, then it means you don't have to produce epsilon or empty string in that language. This is the difference which I told in the previous slide. Is it okay?
okay,
Clear?
sir. Yes, sir.
Okay, so this sentence is saying what? This red sentence, this first red sentence. This sentence is saying that if there is a language L and if there is an alphabet sigma, then the language or the strings of the language that we will produce would be subset of sigma star, nothing else. Because generally a language means the strings of that language. And if there is a sigma star, then strings would be subset of sigma star because sigma star is the all possible strings of that alphabet set. This is because sigma star, this is something I have already discussed. This is because sigma star is what? Is the set of all strings, set of all possible length, including 0, over the given alphabet set. I have already given the example of 0 and 1. I have already, or you can see from here, from these examples, what these examples are saying. Number one, let L be the language. Suppose L is a language of all string consisting of n zeros followed by n1. This can be a question and this can be an answer of that question. So I can ask that give me the alphabet set for the language L, which is a language of all strings consisting of n zeros followed by n ones. Means if the value of n is 1, then 1 0 and 1 ones. If the value of n is, for example, 3, then 3 zeros followed by 3 ones. Are you understanding?
Yes, sir.
Okay. So here this n is in generic sense, in general sense. So we have to give a language and its alphabet set according to this theoretical statement. We have to give a language of all string consisting n zeros followed. Followed का मतलब है कि पहले n zeros आए, उसके बाद follow करे उसको क्या, n ones. उसको क्या follow करे, n ones. So for example, so all string. For example, if n is 0, then number of zeros would be 0 and number of 1 would be 0. So this is the first case, epsilon, when the number of zeros is 0 and number of 1 is 1. And when you give the value 1 to this n, then 1 0 and 1 1, this is the second example here, 0 and 1. And when the value of n is 2, 2 zeros and 2 ones. When the value of n is 3, 3 zeros and 3 ones, and so on. And you can move on. You don't have to give, or you don't have to generate all the strings here. You can write first 4 5 strings and then you can write and so on. So this is the simple representation of a language which is given in this theoretical statement. Another example, this is something you can read it by yourself, because it is LB, the language of all strings with equal number of zeros and ones. The number of zeros and ones would be equal. The position or the ordering of zero is not necessary. Zeros can come first, zeros can come after ones. So there is not some strict condition over the position of the zeros and ones in this language. We only have to take care that the number of zeros and ones would be equal. And the strings are there, you can read it by yourself. Another thing, just to pinch you a little bit, just to, if some student is sleeping, then might be this question will woke him up. So definition is phi. There is another symbol phi, which is coming up in next slides maybe. So phi, which means empty set, by the way. So phi denotes the empty languages. Empty languages. What is the meaning of this phi? Empty languages. So then there is a question that L is equal to epsilon, which is an empty string, not an empty language. So can we say that this L is a phi, is an empty language? So question is, if there is a language L and its alphabet set is containing epsilon, can we say that this language L is phi? Because the definition of the phi is empty language. The answer is no, because epsilon is a string. If there is nothing
Yes.
written here and this is the only curly braces, then we can say that language is phi, otherwise not. So the answer is there already. Now another concept that is called membership problem. This concept or this word will also arise in future lectures, when I will say that this language is a member of that language. So that is basically the membership problem. So, and this is just a representation of that topic, that these kinds of topics can also uh, come in future. So for example, given a string W and that string belongs to sigma star, and sigma star, you know that sigma is an alphabet set and star mean all possible strings of that alphabet set. And from that all possible strings, you are saying that there is one string W and that W belongs to that sigma star. And a language L over sigma is also given. So we have to decide whether or not W belongs to L. So language L is given its sigma star is given, and we are given with the string w, and we have to find that this w is belonging to that language or not. So this is a question of membership problem. We want to find that this string w is a member of that language or not. This is the concept. For example, this w, this string is 1000011, and the question is w belong to the language of strings with equal number of zeros and ones? So if this
Yes,
is,
sir.
yeah, that's good, that's good, that's good. It means that you are understanding, because the number of zeros and number of ones are equal, so this string is
Yes, sir.
belonging to that language. That's good. This gives me real happiness, that it means that you are understanding. But there is some student who was saying that I am not listening your audio properly. What is the condition of that student now?
Sir, they are sleeping.
सर जाग रहे हैं.
जाग रहे हैं.
Sir,
So anyhow, Barajit, this first lecture would be a little bit boring, but from the second language, from the second lecture, I can assure you that maybe, but I can assure you that you will feel something different, because these slides are not mine, so that's why normally when you are teaching from some other material which not belongs to you, then normally uh, then you are lagging behind actually from the actual sense of delivering the lecture. So that is my belief. So, but from the second lecture, the material which I will present, that would be truly uh, mine, and then I am sure that you will get some true understanding. And the further thing is that this first lecture is only giving you concepts about different terms that will appear in near future in this course. So that is also a reason that uh, maybe some of the students will not feel good in this beginning lecture. But anyhow, like Imran Khan, don't worry, don't worry. So you don't have to worry. From second lecture, you will see something different. So finite automata. Now another term. When we will start a topic about regular expressions, then might be at the same time you will see that the machine available for regular languages is finite automata. So here we will see something about finite automata, but before that we have to see what are the different applications of the FA. FA means finite automata. So the application of this theory of automata are simply the finite automata, which is a machine. We can use this concept, or we are using this concept in building software for designing and checking the behavior of digital circuits. For example, the computer scientists, or the electrical engineers who are normally involved in building these digital circuits, they first uh, build a program of that circuit in some languages like Verilog. Verilog is a programming language in which normally we do circuit programming. So, so, so these people are building program first in Verilog, and they are basically coding automata, finite automata like programs to check that how their circuits will behave when they will build it. Then another point is lexicon analyzer of a typical compiler. Normally you have the compilers of C++ and whatever, but in your program you normally give some statements, and how your compiler is understanding that statement, that is the job of lexical analyzer. Lexical analyzer is understanding different words, some of the words as predefined words, some of the words as user defined words, and that lexical analyzer is basically first it builds a logical tree of that statement, and then after that uh, after building that tree, the compiler will understand that what is the order in which different lexical items mean words, strings, then what is the different strings in the statements, in the programming statements that the compiler has to execute. So I can discuss also too much about this point, but I only want to mention that there is some kind of lexical analyzer in your compilers that that normally understands different programming statements in your programs, and that will work in a fashion like finite automata. That is an application of finite automata. Similarly, some other software for scanning large bodies of text for pattern. If you have a large text and you are finding some specific pattern in that text, then this is also an example of a behavior of a finite automata, and so on. You can read it by yourself. So finite automata examples, for example, on and off switch. If you have a simple electrical switch in your house, then the first state is the starting state, and that would can be an off state. When you push the button, then the button would go into another state that is called on state, and this pushing is called action. This pushing is called action, and your button is now in another state that is called on state. If you push the button again, then your button would come in again in another state that is called off state. So this is simple representation of your on and off switch, and this is a simple representation of a finite automata. This is the diagram of the finite automata modeling your on and off switch. Another example, modeling recognition of the word then. For example, this is a word then, and if you have to build a machine that can recognize or that can accept this word then what you have to do? So this is the start state. This arrow, this first arrow is simply giving this information that this is the starting initial state. So this is the initial state, start state. Then you will accept, or then your FA will take input T. After taking T, it will reach at another state that is labeled with T. After that, it will take H and it will reach at TH state. After then, it will accept E only and the state would be D. And after that, it will accept N only and the state would be then, and it is a final state. Double circle is the representation to represent final states in finite automata. This arrow and this state is representing start state. These all things are the transitions, and these different states between initial state and final states are called intermediate states. So what we are getting? We are getting concepts about finite automata shortly or briefly. Now again, structural expression. What is structural expressions? There are two things that you can say these are the structural expressions according to our knowledge of these slides: grammars and regular expressions. These are the two structural expressions. So Grammars, in grammars we have production rules, that is also expression, structured expression, and we also have regular expressions for regular languages. For example, Unix style to capture city name in on Unix operating system. If you want to search city names like this is a city name, Palo Alto, CA. So the regular expression for searching this city in some database is like this. This would be again a problem for you. Might be some student will say that what is the mechanism that this regular expression is written here. Then I will say that if you understand something, then it is good. If you don't understand something, then leave it, because we will start these topics in detail after these all slides of first lecture. So here, this is the Palo Alto CA. So it is starting with capital letter. So you have to write A to Z in square brackets. And in square brackets, A to Z. So any capital letter from capital A to capital Z, any single letter can come here in at this place. Start with this letter. This is the starting. So this is Palo Alto, it's okay, but some word city names can start with W. So that's why it is from A to Z. Again, and then after P, there is a series or sequence of small letters. That's why A, small a to small z, and it is square bracket and it is mentioned with star. And what is meant by star? 0, strings with length 0 or more. So it means that I can produce string 0 after P, which means nothing, or I can produce A, and this star is giving me all possible strings. So A can also be produced, L can also be produced, O can also be produced. So from this combination, I can generate this Palo word. I can generate this Palo word. So my time is finished. So I will now terminate the meeting and I will start it again from here. Okay?
सर आज के लिए काफी है सर इतना।
आज के लिए
हाँ?
काफी है सर।
सर आज बहुत है बस।
नहीं बहुत, मैं अपना पूरा टाइम लूंगा। मैं ज्यादा शुरू नहीं करता, अगर शुरू कर दूं तो मैं फिर तंग बहुत करता हूँ।
मैं तो ये सर